yet?
Nope, I have not watched any NVIDIA presentation.
Do you think you will?
I might. I mean, it depends on what is the content.
New RTX features, how their AI has evolved, yada yada, that kind of stuff.
Hmm. Did you mention AI?
Yeah, they greatly improved it since the 2080 came out.
I can only find RTX in the context of ray tracing, but I cannot find. Okay, let me search that.
It was more on the gamer side, so they went over like how gamers came together and like did like brought their GPUs to model COVID and stuff like that,
Hmm.
and what the future of their AI is going to do.
Hmm. Interesting. So I would assume that's a neural net based type of AI.
Probably. Honestly, I don't know how their AI works. It's quite interesting though.
Hmm. Okay.
Yeah. So they went over how the folding team was able to use over, I think it was like 5 million GeForce and RTX graphics cards to model COVID within like 3 months, and figured out that it was transmitted via breathing.
Hmm. Okay. Well, that's kind of interesting. All right. Oh, okay. So Joshua, mentioned something like that too. Folding. Okay. All right. So it is almost time. We got about 10 seconds to go. I hope everybody had a chance to review the content from last Thursday, because I did. So I know where we can start today as a result of that. So I rely on my own class recording to remind myself, where I need to get started with. All right, so I'm gonna get the module started here. There was one report of a typo, which I fixed already, so that's good. And we are down to the last two operators, and they are used to compare sets. Okay, so these are the two that we haven't talked about yet. It is time, so the time is 10:30. So what I'll do is I'm gonna help out people who do not have time to attend the class because they have conflicting schedules. But they also have a whole lot of other stuff to do, so they may not have enough time to go over the entire lecture just for attendance purposes. So the word of today's attendance is enrollment. Okay, so I'm gonna pull this right next to here so it's easier to see. But now I have to hunt for the text terminal that is actually responsible for the content of this. All right, so where did I put that text terminal? I have 5 or 6 text terminals and each one has multiple tabs on it. There we go. Okay, so I was testing a few features earlier. So I was testing whether I can make tables out of Markdown and whether I can use multi-line equations in Markdown as well. So yes, as you can see, they're both doable. So I'm gonna leave those floating around for a little bit, even though they might be slightly confusing. But the role taking quiz, the word for today is enrollment. Okay, so it's a reminder for all of you to check your roster, to check your enrollment, to make sure that you're still in class. Some people are on waitlist and some people are not on waitlist. So it's good to good to check your e-services just to make sure that you're still enrolled in this class. Okay, if there's something that is not right, okay, you need to let me know and we'll try to get those things fixed as quickly as possible. Okay. All right, so with that done, I see one concurrent viewer on YouTube. So I just want to remind people that YouTube is lagging behind quite a bit more than Discord, which means, when I ask whether people have questions or not, it's much harder to respond to Discord when people are watching it through YouTube instead of using Discord. So that's just a point. There's some, yeah.
Question about the set theory quiz. I accidentally started it instead of the roll for the quiz. How many
Yes.
questions do we have on that?
On the set one, did you submit already?
Yeah. No, I did not.
Well, as long as you don't submit, you're fine. So
Should I close it and then reopen it, or should I just
yes, you can close it and then reopen. But when you reopen, I don't think this one has a password to protect it, so you can just reopen it and you will continue from your last the last time you turned in something in the quiz. So yes, you can continue to work on it, but once you hit submit, that's it. So don't hit that submit button unless you're absolutely sure that you're ready to hit the submit button.
sounds good?
All right, good. All right, so I got this taken care of. And now we can go back to talk about subsets, okay? So this little operator here that looks like a U that is turned sideways with a bar under it, it's called subset of, okay? So in this case, this expression is A is a subset of B, okay? So this entire left-hand side of the equivalence or if and only if is saying we're basically defining the symbol of subset of using symbols that we are already used to. Okay, so we are using the minus, which means we are looking at a set that consists only of elements that are in A but not in B. So as long as that set is empty, then we can say that A is a subset of B. Okay, so do we have any questions about this notation, the notation that I'm pointing to? A is a subset of B if and only if A minus B is an empty set. Any questions? I'm looking at the text on the side and there doesn't seem to be any questions. All right. Okay, no questions about that. All right, so we're going to move on. Okay. Oh, by the way, the other way to look at this is there's nothing that is in B that is not in A. Okay, let me rethink that. A minus B would be a set of elements that are in A but not in B. And if it is empty, that means there are nothing in A that is not in B. Okay, I have to correct myself. There's nothing that is in A that is not in B. That makes A a subset of B. All right, so let me just test to make sure that we all understand this concept. So we're switching to the whiteboard area, which I am, okay, I need to keep this window down here. You cannot see it, but I need to kind of make it more clear. Okay, so let me ask you about this. So we got this, and then we have this, and then we got this again. All right, so when you look at this expression, is it true or is it false? Okay, so I'm going to say, is it true or is it false? You can either use voice to answer the question, or you can just go ahead and, it is true. Very good. Because there's nothing in an empty set that is that cannot be found in another empty set, because an empty set has nothing. So an empty set is a subset of an empty set is true. Does that make sense? Because yeah, go. Okay, so let's look at another thing then. Okay, so let's look at this instead. So let's look at this minus this. Okay, so I need to put in a new line. So there we go. All right, so can someone tell me what is the answer to this question? What is in an empty set in the first empty set that is not found in the second empty set.
It would be the same.
No, wait. Okay, but what is the same?
Oh, both are empty sets. The empty set minus the empty set will result in an empty set.
That is correct. All right. So because an empty set minus an empty set is indeed an empty set, it met the requirement that we were just talking about before, because we have an empty set being A, we have an empty set being B. Empty set minus empty set is indeed an empty set. So when the right hand side of if and only if is true, then the left hand side has to be true too. And that's why we know that an empty set is a subset of an empty set. Is that okay?
I think I understand it, but you mind if we clarify a little bit?
So if you go to the next, in the next paragraph, it clarifies it pretty good.
Okay, so let me point to the next paragraph, which is this part. This means that A is a subset of B if and only if there are no elements that are in A but not in B. But if you look at an empty set has nothing, right? So if an empty set has nothing, then there's nothing in an empty set that cannot be found in another empty set. And as a result, an empty set is a subset of itself.
So by technicality, wouldn't every empty set be a subset of any other set?
That is true as well. Okay, so let's look at how we can express that. Okay, so let me switch to the whiteboard area. Okay, so now we can say regardless, oops, typo, regardless of how a particular set A is defined, an empty set is a subset of A is true. Yep, that is also true. An empty set is a subset of every set, and that includes itself. All right, does that make sense? Because an empty set is not, there's nothing in an empty set, okay? So it automatically meets the requirement that nothing in an empty set cannot be found in the other set. In other words, you cannot find something in an empty set that cannot be found in the other set. Is that okay? Or is it still kind of confusing?
I think I understand the concept. I just don't like the way that it's worded, I guess.
You don't like the way it is worded.
I think that maybe it's possible to make it a little more clear. Reading further on, it makes more sense.
Mm-hmm. Okay.
It wasn't immediately obvious to me.
Okay. So let me ask the question. Which part do you not like? The definition of subset of?
Yeah, I guess it was just the definition. When you say that there are no elements in one that are not in the other.
Yes.
Yeah, it just wasn't immediately apparent to me. But just writing it out to me, and then it made it a little more clear. I guess I'm a visual learner or whatever.
Okay. So if you're
Yeah. Would be A is of B, and nothing in, or everything in A will be in B, but not everything in B will be in A.
not yet. Okay, so that would be a slightly different but related expression or operator. But right now, a set is its own subset. Okay, are we good? Because A minus A is always an empty set. If you instead of using B over here, then we can say regardless of which set A we're using, A minus A is always an empty set. Let me make that point over here and see if it is clear to all of us. Okay. So now I will also say regardless of how set A is defined, A minus A is always empty. Does that make sense to you, to everybody? All right, cool. All right, so I'm looking at the text here. So that also meets the requirement of A is a subset of A, regardless of how you define the set A. It is its own subset. All right. Okay, so I'm not seeing any questions in the text channel. So now we are going to define a slightly different operator, but it is related to the operator that we just talked about. This symbol here is a proper subset of, okay? So this is basically reading as A is a proper subset of B if and only if A is a subset of B and B minus A is non-empty. In other words, there is something in B that is not in A. So the first requirement, which is A is a subset of B, means everything in A can be found in B. But this is a conjunction, which means, and on top of that, there's something in B that is not in A, because we are looking at B minus A being not an empty set, which means there is something. There's at least one thing that is in B that is not in A. Okay, so is that definition okay? Does everybody understand the definition of A? What is a proper subset of?
Yes.
Okay, excellent. So I'm seeing some text channel confirmation as well. So that's all good. All right, so now we have one last operator. The last operator counts the number of elements in a particular set. So in my text here, I'm using the same symbol as what in a different context would be seen as the absolute value. But in this case, the bar, is the cardinality, which is basically asking what is the number of elements in a particular set. So if we want to use a concrete example, when we look at a set where 2, 4, 6, 8 are elements of that particular set, then the cardinality of that set is 4, okay? Because we're just really counting. Are we good so far?
If we make
Mm-hmm.
that set of 2, 4, 6 equal to x, and then the cardinality of x would also equal 4.
Say that one more time.
So if we make x
Mm-hmm.
set of 2, 4, 6, and then get the cardinality of x, that will also result in 4.
If it's just 2, 4, 6, then it will have a cardinality of 3 and not 4.
Or 6, 8, sorry.
Oh, 2, 4, 6, 8?
Yeah, if you make the x equal to that set, and then get the
Yeah,
cardinality.
yeah. So we are, so you can use x, as a symbolic name. So we can just refer to the symbolic name. So in other words, if you say let x equals to a particular set, in this case, I'm going to use exactly the same example. So 2, 4, 6, 8. Okay, then you can now say, the cardinality of x is 4. So it's really just using a symbolic name instead of spelling out the literal constant, so-called literal constant of the set. So yes, that is good. So now we got some really kind of interesting things. I'm just going to put it out here, but I'm not going to explain, any further until later. Okay, but I'll put it out here. Okay, so I'm going to say let this be the set of all integers. Okay, sounds pretty simple, right? And then we'll use another example here. We'll say let E be the set of all even integers. Okay. All right, so Z, the funny looking Z is the set of all integers, and then the letter E uppercase is the set of all even integers. Okay, so one is all the integers and the other one are all the even integers. So when you think about these two, okay, it is pretty clear to us that the cardinality of E is what? Oops. Yep. INFTY. Yep, there we go. Yep, it is infinity. Okay, there, because if you say, oh, this is the set of all the even integers, then I'll take the largest of those integer values, and then I'll ask, what about this plus 2, right? Oh, that's another even integer, so that means that there's no end to it. Okay, so yes, so Alex, you're right too, it is infinite. So when I ask you what is the cardinality of the set of all integers, well, it is also infinity, right? Because that's the same thing. INFTY. Why is it? Oh, okay, I can see. I put the and dollar sign at the wrong place, and then I need a bar over here. Okay, but that's pretty clear too, right? Because the set of all integers also has an infinite number of elements. So now here comes the fun part. Okay, so the fun part is, what about the difference between these two? Okay, if I look at z, the funny looking z minus e, this is also infinity. INFTY. Does that make sense? Because if you take out all the even integers from the set of all integers, then you're left with all the odd integers. But the set of all the odd integers is also has an infinite number of elements. So we now start to look at things and go like, whoa, but that's just really odd, right? More interesting stuff. Okay, so we can look at math BBR. So this is the notation of all the real numbers, and then minus math BBZ. Okay, this is also infinity. So the funny looking R is the set of all real numbers, and then Z, once again, is the set of all the integers. So when you look at the difference, okay, it is also an infinite number. Now, it is infinite in a very strange way as well, okay? If you just take any two integers, even adjacent integers, like between 1 and 2, there's an infinite number of real numbers between those two already. So we are looking at, when you look at the cardinality, sometimes, it looks like things start to look very interesting. Okay, I'll just put it that way. So we'll get back, okay? In fact, we'll get back to this one over here. We'll get back to the cardinality of all integers probably in about 1 or 2 lectures. We'll get back to this one because it has something that is particularly interesting from the point of view of computer science. Okay, so we'll get back to this one. But I do want to introduce all of these kind of interesting conclusions of when we look at the difference between two sets, each one having an infinite number of elements. The difference, okay, which is a set, can also have an infinite number of elements. So that part is can be very interesting. All right, so we are done with module 0280, and now we are moving on to quantifiers. So quantifiers are, guess what they're useful for? They're useful for quantifying, okay? So we have 2 quantifiers, but we'll see later on that we only need one of them, but it is handy to have both of them. Okay, so quantifiers basically they already apply to everything in the universe. So when we use quantifiers, they're basically applying to everything in the entire universe. So that's okay. It's kind of abstract, so we'll get to that part later on. So to make our discussion more concise, we can use a variable x to refer to a thing that we are examining, and p of x is some kind of Boolean function, otherwise known as a predicate. We introduced the term predicate before already. So p of x is a predicate that applies to x. So this means depending on what x is, p of x is either true or false. So to say that everything in the universe makes p of x true, then we use the following expression. For all x, okay, so this inverted A symbol is known as for all, or if you want to look at it, in a slightly different way, you can say every, okay? So every, for all, they're all basically referring to the same thing. So this basically reads as for all x, and implicitly from the entire universe, P of x is true, okay? Now, if that is true, then this entire expression is true. So for all x, Px is not a statement saying that it is true. It is an expression that can be true or false. Okay, so so this is really just repeating what I just said a little bit earlier. For all x in the universe, P of x, and then if I don't say anything, then it is implicitly is true. Okay, if I want to state that this is true, then I wouldn't say that this is true. I would just simply state this. All right, so the other operator or the other quantifier is known as there exists. It looks like E. It is also kind of inverted, but in a different way. The A is inverted vertically, but the E is inverted horizontally. So left, right, inverted. So this one is basically saying there exists X such that P of X is true. Okay, if I don't say anything about this entire thing, it is implicitly saying it is true. So do we have any questions about the for all versus the there exist? Okay. So if you want to look at this one, it is the same thing as saying for every x, P of x is true. If you look at this one, it is saying there exists at least one x such that P of x is true. So you can also look at the first one as every, look at the second one as at least one. Okay, so that's another way to look at these two quantifiers. The first one is also known as the universal quantifier, and then the second one is also known as the existential quantifier. So they're just kind of different names to refer to the same thing. So we clear on these terms? Okay. If there are no questions, then we're going to move on. So we'll use negation in conjunction with quantifiers now. Okay. So what if you want to say none? Okay, the English word none. How do we use that? Or sometimes we say no. So let's go ahead and look at some examples. So I'm switching to the whiteboard area to look at some example here. Okay. So we'll go ahead and use start with an English statement that says no one lives forever. Okay, so I just want to express exactly the same thing. So I'm not stating whether no one lives forever is true or false. Okay, I'm simply trying to find an equivalent logical expression that says exactly the same thing. So the first thing I need to do is, to make it handy, I'm going to define the predicate. Okay, so we'll go ahead and define predicate P of x so that P of x is true if and only if x lives forever. Okay, so it's really just instead of referring to the phrase living forever, I'm defining a predicate so that P of x is true if and only if x lives forever. So it's just a symbolic thing, okay? Because I don't want to use the phrase lives forever every place. So P of x is a whole lot easier to type. So that's why I'm defining the predicate. So now we can now say no one lives forever is equivalent to, now we want to just use logical operators. So we can use existential, we can use universal, we can use the inverted E, we can use the inverted A. we can use all the logical operators that we have defined up to this point. Okay, so that includes negation, conjunction, disjunction, implication, and equivalency. Okay, so now what do we do to define that expression?
Hold on. If with two F's is if and only if, correct?
Yes, IFF is if and only if. All right, so let's go ahead and get started, okay? So we'll go ahead and look at something that may not be correct, okay? So we'll say, all right, so let's start with for all, okay? So we'll say for all x, p of x, okay? So what is that actually saying? What is the English equivalence of for all x, p of x?
For all x that exists, x will equate to true.
Well, Omar is right. Everyone or everything in the entire universe lives forever. So that includes people, living organisms, but it will also include non-living organisms. It will also include the hydrogen atoms. It will include neutrino subparticles. You know, because it is, remember, for all is universal, as in everything applies, okay? So no one lives forever is kind of equivalent to for all x p of x. So we'll later on we'll try to figure out, okay, but how do we filter out that we're only referring to people, okay, or we're only referring to living things, okay? So we'll talk about that later. But right now we'll just say that we'll just let this one slide, okay? But it is not meeting the requirement, because for all x p of x means everything in the entire universe in the entire universe lives forever. Okay, so that's not quite what we want. Maybe we can just fix this using a negation. Would that work? Well, let's think about it this way. Okay, the negation is applied to the entire expression. In other words, if I were to use parentheses to indicate the ordering of the operators, the negation is on top of everything. In other words, we're saying it is not the case that everything lives forever. Does that capture what we want to say? What we want to say is no one lives forever, which means everybody dies, right? So what we have here as an expression is saying not everyone lives forever. But maybe there are a few people who do live forever, because that's all it's saying. Okay, it's saying that not everyone, it is not the case that everyone lives forever. Okay, so Omar has got the right answer. Okay, or one of the right answers, I should say. So Omar is basically saying, let's move the negation. Okay, let's take the negation out of here, and instead we'll apply it over here. Oops. Okay, I put the negation symbol at the wrong place. So negation here, and there we go. So I'm just repeating what Omar has typed in Discord. Okay, so let's look at this one. This one is saying for everyone, okay, for all x, okay, it is not true that x lives forever. So it is basically saying everyone does not live forever. Okay, well, that works, right? I mean, this really means the same thing as no one lives forever, because it is inverting the logic to say that everyone does not live forever. Does everybody see, you know, how these two are the same? So let me just kind of write it in English here. No one lives forever is the same thing as everyone does not live forever. Can everybody see how these two are the same?
I have a question about, I guess, like the universal and the existential.
Mm-hmm.
So, as far as negation is concerned, um, is it fair to use the negation of the existential and the universal? Because from what I'm understanding, you can say that there isn't a single instance of something, or there are
Mm-hmm.
no instances of something. Are those two terms equivalent? Because it seems like they are when you write it.
Mm, it depends on where you attach the negation. So we're not quite done with this one yet, okay? But right now, I just want to emphasize that no one lives forever, which is the original English sentence that I want to present in logical terms, is the same thing as saying everyone does not live forever. Is that okay? Yeah, go ahead. Go ahead, Joshua.
Are you being very careful to say like everyone, or like to use this universal term in a way?
Yes. So I'm trying to match this, to use everyone is referring to the for all symbol, and then does not live forever is referring to the negation of P of X.
Okay, I see it.
All right. So now we're gonna catch up with the Discord discussion because the Discord discussion is actually slightly ahead of what we are actually talking about. So the Discord discussion is basically saying, well, but is there a way to use existential in this case? Okay, so let's check out how we can express exactly the same thing, but using existential as an expression. Okay, so I'm going to copy and paste a little bit here. So initially it is the same thing. So what I'll do is I'm going to present the simplest existential expression first, and then we'll go ahead and modify it so that it is going to it will express exactly the same thing. Okay, so right now we see there's no equivalency at all, right? Because if I want to express that no one lives forever, then the logical expression is definitely not saying that, because the logical expression is saying there's at least one person, there's at least something that lives forever. That's basically what it is, right? Because this is there exist. So the logical expression is saying there exists at least one thing in the entire universe that we call X, such that P of X is true. Okay, so that's definitely not doing what we wanted to do. So now we can say, well, maybe we need the help of negation. So we'll go ahead and try to put the negation on the outside first. And now we say, well, is this saying the same thing as no one lives forever? What do you guys think? I think this one is saying it is not the case that there's at least one thing that lives forever. The question now is that equivalent to saying no one lives forever? So what do you guys think? This is not a theology class, so I'm not asking this question in a philosophical sense. I'm asking this question in a logical sense. Well, I mean, yes, I can put it right next to the left-hand side of the there exists symbol, but I'm using the parentheses to emphasize the negation applies to the entire thing. Nope, they're the same. Whether I put it inside the parentheses or outside of the parentheses mean exactly the same thing. Because negation always applies to whatever is immediately to its right-hand side. So if whatever is to its right-hand side is the there exist, then we are negating the entire there exist operation, which is the same thing as negating the there exist, but in parentheses. So they are equivalent. Whether it is right next to the... Okay, let me more clearly state what I mean by that. So if I remove the outermost pair of parentheses, it really has not changed the meaning of the expression. The extra parentheses are only there to emphasize that we are negating the there exist operator. Yep, there we go. But is everybody buying this? That the phrase of no one lives forever is meaning exactly the same thing as it is not the case that you can find at least one thing that lives forever. So the question is, have we established that particular equivalency? Okay, so I'm not seeing anyone asking questions or saying, we need to use more time, okay? But here's the fun thing, okay? So the fun thing is using this as an example. Now we can see how these two expressions are really the same. Okay, I need to resize my text window on the side. You cannot see it, but I need to make sure everything is in the same window. So now we can say, if you want to say for all x, it is not the case that p of x is true. Okay. And I'll put an overall parentheses around the entire thing. Okay. So this expression turns out to be the same thing as the next expression. Let me put it here. Right, left. Okay, I think it has to start with left. Left, right arrow. So it's really the same thing. It's if and only if. And in this case, we have the negation of there exists x such that p of x is true. There we go. Okay. So let me point to the finished expression here. So on the left-hand side of the equivalency, which is also known as if and only if, okay, we have for all x, it is not the case that p of x. In other words, we're basically saying for every x, p of x is false. It is really saying exactly the same thing as it is not the case that we can find at least one x such that p of x is true. I think I got one too many close paren here. There we go. Okay, so these two expressions are actually the same, and Omar is also correct. You can put a bar across the there exist. That is also meaning the negation of there exist. And I think they have one for all too, which is a bar through the for all. But I do not use the a bar for the negation of an operator, just because it is more clear to apply the negation on the outside. And this way we don't have to memorize as many symbols either. But Omar is also correct that in some other textbooks you will find the symbol of there exist with a bar across it, which means it is not the case that there exists blah blah blah. Are we good so far? Do we have any questions about the concept of there exist, which basically means at least one, versus for all, which is basically the concept of every? Are we good? Looks like we're good. Okay. But somebody's going to say, well, but if this is true, okay, when I say this, I'm referring to the last if and only if expression here. If this if and only if is true, that means one of these two quantifiers is really not needed. Okay, if we are allowed to use negation, then we can get away with just one of them. Okay, so I'm going to express another equivalency right below this one, and then you guys can tell me whether that makes sense or not. Put the negation over here and get rid of the negation over here. And I'm just counting the parentheses. Okay, let me move the parentheses over here. All right, does that make sense to all of you? See how I just use a quantifier? Does this make sense to all of you? I did not ask, does it make sense to at least one of you? And this one is actually pretty easy to see why it is the case. Okay, so if anyone wants to find out, but why I cannot see how it applies, okay, so let me just make it super duper too many parentheses on the right. 1, 2, 3, 4, 1, 2, 3, 4, right? Not enough close parentheses. Okay, there's one more. And that means the other one also needs one more. There we go. All right, there we go. Okay. All right, but how does this make any sense, right? Okay, so let me work on this step by step. Okay, it's really kind of important to work on things step by step when we don't see, how it can go in one single step. So we'll go ahead and work on this step by step. I'm just thinking about how to format this, because I want to format this and make it look nice. So we'll give this a try. Okay, so I think this works. I'm using a LaTeX environment called an array. There we go. And then we'll put this inside here, but it won't need the extra stuff here. And to make everything look aligned, I will do that. And then we use a new line symbol like that. All right, so here's the next line. So in the next line, what I'm going to do, in fact, I'm going to start with whatever we have over here, okay? Because if we have already established that, we'll just go with that, okay? So we'll make this one having no negation on this side and have a negation on this side. Uh-oh, it doesn't like that. What? Oh, okay, I see why. There we go. All right, so this first line here is exactly the same thing as what we have here. I see that I moved the negation, so let me fix the negation location so that they are exactly the same. There we go. All right, so can everybody see how the first line is the same thing as what we have already concluded? Are we good? All right. Okay, very good. So now what we'll do is we'll do a double negation. So I will keep the negation that was here, and then on both sides I put an extra negation. So now you can see how the left hand side of the if and only if now has a negation, and then the right hand side of the if and only if also has an extra negation. So do you see how these two statements are the same? If I put a negation on one side and I put a negation on the other side, the if and only if will continue to work. Is that okay? Okay, very good. So now on the last line here, we're going to look at the double negation and go like, but Tech, that is just a waste of space. Double negation doesn't do a single thing. So let's get rid of both negations on the right hand side of the if and only if. Do you see how we arrived to the last line? How this is all step by step? How we looked at this double negation here and just removed the double negation, because double negation doesn't do a single thing. All right, so yes, everybody's got it. But the conclusion is kind of interesting, because the conclusion basically says, if you really just want to express there exists, guess what? There's no need to use the symbol there exists. You can just say it is not the case that for all blah blah blah, and then negate the predicate also. Okay, so that means, out of the two quantifiers, if you are allowed to use negation, out of the two quantifiers, you can use just one of them, okay, by using negation. But, okay, meaning that, yes, we can do this, but at the same time, I think, there exists x, p of x is a lot more clear compared to it is not the case that for all x, it is not the case that p of x is true, okay? So from the point of view of easier to understand, it is nice to have both quantifiers. But from the strict perspective of, in logic, do we need both quantifiers? The answer is no. We can use just one of them and then use negation to basically have the same effect, to get the same effect as the other one. So that's the fun of logic, okay? A lot of stuff, that we think it's nice to have these two. Well, the answer is yes, it is nice to have these two, but it is not necessary. Okay, it's just like, between not and or, okay? Those are three distinct operators that we learn in C, C++, and just about any programming language. And as it turns out, if we introduce the logical operator called NAND, negated AND, we don't need not, we don't need and we don't need or either, okay? We can just use NAND, okay? And on top of that, we can use NOR, okay? So NOR, which is negated or, and NAND, which is negated and, they have equivalent expressive power. In other words, either one can be used to implement every other operators that we know of. All right, so are we doing okay so far with quantifiers? Okay, looks like that is the case. So we head back to the module, and now we talk about filtering. Okay, I call this filtering, but you can call it anything you want. Okay, because a lot of times we don't want the predicate to apply to everything in the entire universe. Okay, so let's look at an example here. So we switch back to the whiteboard area, and this time we want to say okay, so we'll put it this way. So we'll say at least one professor at ARC knows what he/she is talking about. And just to be politically correct, I'm going to use they. Okay. Just, and also, this is also because I don't want to type he/she. There's more keystroke in it. Okay. Do we use are even if I use they as a singular? Is that true? But that would not, but the R is not going to go well with knows. How do we reconcile that grammatical disagreement? Okay. I genuinely does not know. Okay, I genuinely do not know how to reconcile the singular verb versus the plural noun. So I'm gonna let Aaron and Catherine and Joshua to let me know. Okay, is this they are, but I agree it is confusing. Remove is. Oh, okay. Okay, how about rephrase this? How's that? Better? We'll just avoid the use of verbs. Goof is okay too, Aaron. I think I can go along with goof too. So goof or good, I think we're ready to go. Ready to proceed. Okay, there we go. They all work and none of them work at the same time. All right, so if we want to say at least one professor at ARC knows their stuff, then we can first define the predicate of knowing their stuff. Okay, so we'll define, okay, we'll go ahead and use a different symbol. This time we'll use Q. So we'll define the symbol Q of X to mean that if and only if X, whatever X is, knows their stuff. Okay. So X can be Catherine. Okay. X can be Joshua. X can be whoever is working in the cafeteria, okay, can be a staff member. So we are not limiting what X is, okay? So the predicate applies universally to everything in the entire universe, okay? So now the question is, how do we apply this now to say at least one professor at ARC knows their stuff? So I'm going to start off with something that is not going to work, okay? So I'll start with something that seems to make sense, but it doesn't work, okay? So we'll say exists X such that P of X, okay? Q of X, sorry. There we go. And we know this doesn't work because X is a universe. X applies to everything in the entire universe, which means this statement, okay, this statement over here, can be true while at the same time no professor at ARC actually knows their stuff, okay? Because guess what? A professor from Sac City, a professor from CRC, consumers, a professor from FLC, they're all in the universe, right? So there exists one thing in the entire universe such that that thing knows their stuff. Doesn't say anything about professors at ARC, okay? So in order to express this, now we need to define a set first, okay? So we'll go ahead and define a set, okay? So we need to say define a set. Let's call it A is a set of all current professors at ARC, okay? Aha, so now that we have a notion of this particular set that I call A, now we can express what we originally wanted to express, okay? So we can now say, oh, okay, here's the other thing, okay? Because this X here can apply to everything, so that also applies to neutrinos, okay? Neutrino is a subparticle, is a subatomic particle, okay? Does it really make sense to say that a neutrino knows its stuff, okay? Doesn't make sense, right? So the predicate may not even apply to certain things in the entire universe. It is neither true nor false because a neutrino is not something that knows or not know something, okay? As far as we know about neutrinos, of course. So that means we want to change the phrase to something slightly different. So this is the modified expression. So we'll say exists X. So when we type this part here, this X is still being applicable. I can bind anything in the entire universe to this X here. But inside the parentheses, now we can use something to help us limit the scope. Or, as I use the word in the notes, it's called filtering, okay? So we'll use, I'm typing this in a strange way because I usually forget about parentheses. So I'm gonna type it in a way so that I do not forget the parentheses. All right, so it uses the implication. That's not implication. That is an implication. There we go. So it uses implication. So the right-hand side of the implication, the consequent, is Q of X. Okay, so we know Q of X has to be somewhere in here. So this is where it goes. But the left-hand side, sorry, the left-hand side of the implication, the precedent, now needs to specify a filter. In other words, if something doesn't meet this requirement, don't even bother to check whether Q of X is true or not, okay? So that is where we use the in operator. We say X is in the set of A. So now we have this expression. And let's go ahead and look at this and see what it means, okay? So in English, okay, it means there exists at least one X such that, okay, X is an ARC professor implies X knows their stuff. Okay, That is basically the English equivalent of the same statement. And I'm still using the word implies, okay? So the word implies can be changed to the negation of the left-hand side or the right-hand side non-negated. So let's go ahead and change this statement here so that we use the definition of that. Okay, so all I'm doing here is to get rid of the implication and turn it into an or, but in order to do that, I have to negate the left-hand side. Okay, so these two are equivalent. Okay, it is just that one uses the symbol that we call implication, and the other one uses the definition of implication, so that the implication operator is now being used, being redefined using more elemental operators, which is the negation, which only applies to the thing that is immediately to the right-hand side, and then an or of the other side. Okay, so when we look at this, okay, let's focus on just this part, the highlighted portion, but without the quantifier. Okay, so if I say let's bind this lowercase x to our sun, okay, sun as in the shiny object in the sky. Okay, so if we bind x to the sun, to soul, okay, then what is the outcome of that? So the first question is, remember x is bound to soul, the sun. So the first question is the sun an element of the professors at ARC? That's a stupid question, right? The answer is no. Okay, well, we take the negation of that. Okay, so that means the negation of the left-hand side of the or is true, because the sun is a professor at ARC is false. So the negation of that is true. So when you use short-circuited evaluation, I hope all of you know what short-circuited evaluation is. Okay, that means I don't even need to bother to evaluate the predicate, because the expression to the left of the or is true already. I don't need to evaluate the part to the right-hand side. Is that okay? Does everybody see how I just used implication, which is this thing here, to limit the scope and say, I don't really care about anything other than professors at ARC. If it's anything other than professors at the ARC, we'll just say that, forget it, okay? We are not concerned about it. Okay, excellent. So we only care about professors at ARC. So this is now, basically, okay, let me go back to this one here. So this is how I apply filtering to basically say, let's not think about everything under the sun or in the entire universe. We just want to focus on certain things, okay? Things that are elements in A, and other things we don't care at all. Okay, so now let's go ahead and take a look at this one. Okay, I'm just copying and pasting here. So I'm copy and pasting this one, and I'm just going to say there's a shorthand to it. Okay, so I'm going to use left, right arrow here. So I'm going to use a shorthand here. The shorthand is exist x in A, and then P of x, Q of x, sorry, Q of x. There we go. I'm just looking at the matching of the parentheses. Okay. So that's just really a shorthand. So instead of using the implication, I'm now saying we only want to look at things that are in A, and I want to see if there's at least one thing in A such that Q of x is true. So it's just a notation thing. We are really just looking at the notation that started off with something that's kind of long and more complex into something that is a little bit shorter. Do we have any questions about the shorthand of there exists x in A, Q of x, which is now basically you're saying there's at least one professor at ARC who knows their stuff. Once again, this is a statement. It is a condition. It is not necessarily true or false. It is something that has a true-false value. So it is entirely possible that no ARC professor knows their stuff, okay? It's entirely possible, okay? The statement doesn't say that it is true. The statement is only giving you a condition, an expression that can be true or false. All right, so I will give you guys like 5-10 seconds or so to see if there are any questions, and if there are no questions, then we're going to continue to talk about how we use quantifiers in the definition of set operations. I'm just looking at the clock. All right, I'm not seeing any questions. All right, so I'm seeing 2 people watching the live session from YouTube. So I just want to bring up that reminder again that YouTube is lagging behind quite a bit. Okay, so just want to get that cleared up. All right, so moving back to the module. So we are pretty much done with the discussion of quantifiers. So now what we'll do is we're going to go back to our notes here, and we'll go back to set theory, but this time we'll use quantifiers to look at the same things, the same stuff that we have been looking at. And this would be a good time to also remind everybody that the set theory homework is open. Okay. Now, Aaron, actually mentioned that at the very, very beginning of the lecture, but I want to remind people again that you do have a homework that is due on Thursday, okay? But you can spend as much time you want on it as long as you do not submit and it is before the due date, okay, which is 10:30 a.m. on Thursday. Okay, so you got 2 days to work on it. A little bit less than 2 days, because by the time you hear about this, it's already past 10:30. All right, so we're going to move on to set theory using quantifiers.
But they're good guys.
So we'll go ahead and pull this out on its own. There we go. So there's a rationale behind why we are revisiting stuff, okay? Because this time we want to look at things from the perspective of using quantifiers. Now quantifiers are very, very useful.
Not the point.
Okay. Thank you, Aaron. Aaron is mentioning who is watching from YouTube. I see there are 4 people now, using YouTube. There are 4 concurrent viewers on YouTube. So it's not just Yalas who's watching from YouTube. So there are 4 people watching from YouTube at this point. It's possible that some of these people missed the beginning because they had other engagements or other obligations, and they're watching from the beginning. So that's entirely possible. But I do want people to know that YouTube streaming, live stream, is not really that live because of the lag time. Okay, so the first thing we are revisiting is the concept of equivalency. So given 2 items X and Y, how do we determine whether they are the same or not? In other words, how do we evaluate this expression X equals to Y? Now, when we use X equals to Y in logic, it is not an assignment operation. We are not changing X to the value of Y. We are actually comparing X and Y and to see whether they are the same or not. In other words, in a context of logic, not programming, a single equal is actually the same as what we see as a double equal in programming. Okay. All right. So having that cleared up, we are going to see if one is a set and the other one is not. Okay. In other words, if you look at X, Y, and one is a set but the other one is not, then we automatically say that X equals to Y is false. Okay, that kind of makes sense, right? Because we are looking at a folder on one side, we're looking at a file on the other side, and we ask, are these two things the same? No, they're not the same. One is a container, and the other one is just a regular file. They cannot be the same. So the next one says, okay, given that they are not, okay, out of xy, it is not the case that one is a set and the other one is not a set. Then we want to ask, are they both not sets? Okay, is x an integer and y is an integer? Is x is a real number, y is a real number, and so on. So if x is not a set and y is not a set, then we use the normal comparison. Okay, so we already know how to compare, say, integers or real numbers and stuff like that. So we'll just quote unquote use the word normal to apply to things that are not sets. Okay. So now the third one is saying, what if x is a set and y is also a set? Then how do we determine that x equals to y? So this is where we use equivalency, and we also use quantifiers. Okay, so we at this point we have already confirmed that x is a set and y is also a set. So this is basically saying x and y are the same if and only if, okay, this conjunction is true. So what is this conjunction saying? It is basically saying everything in x is also in y, and everything in y is also in x. Does that make sense? Does that make sense to you that if x is a set and y is a set, these two things, these two sets are the same? If you look at everything in x, it can also be found in y. If you look at everything in y, it can also be found in x. Okay. The slightly more concise way to say it is to say x equals to y if and only if for everything in the entire universe. Okay. If it is in x, if and only if it is also in y. Okay. That really is saying the same thing, just a whole lot more concisely. Because if and only if, which is what this left-right symbol is basically saying if whatever is to the left-hand side is false, then whatever is to the right-hand side better be false too. Whatever is to the left-hand side is true, whatever is to the right-hand side better be true too, and it's the other way around as well. Okay, so that means, if something is in y, it better be in x. If something is not in y, it better not be in x. So it's really saying exactly the same thing as before. Now, if you say, but Tech, I think we have another way to say something like this, but without using quantifiers, we can use set operations that we have already been shown. The answer is actually yes. Okay, there's a way to define it using just the minus operation. Okay, so let's go ahead and take a look at how we can see that. So given that x is a set and y is a set, then x equals to y. Okay, let me put in parentheses, x equals to y if and only if the following. So we want to use the minus symbol. Okay, so we'll say something and something over here. Okay, so we now go back to the first one and we say x minus y is an empty set and y minus x is also an empty set. Oops, you're not seeing the empty set because I forgot to escape the braces. Because if I don't escape the braces, braces have special meaning in that format. There we go. All right, so does that make sense? If x and y are both sets, okay? Because otherwise, set operations cannot be defined. So if x and y are both sets, okay? And it turns out that everything in x is also in y, and everything in y is also in x, then x and y are the same. So it kind of makes sense, right? All right. I'm just looking at the time here. We got about 8 more minutes. Oh, one more thing. Don't forget to send me the prerequisite and co-requisite requirement challenges. As far as prerequisite is concerned, only certain people need to send me something because I could not use the automated prerequisite checker to find that they have met the requirement. As far as co-requisite is concerned, everybody needs to send me something. If you have sent me something already and I haven't replied, you can just give me a nudge and say, okay, I sent you something, please go ahead and review it. But if you have not sent me something, then you should probably get started with that in that process. All right, so moving on to section 4. So section 4 is using this notation, E, which is, in the example, E was the set of all integers, even integers, x such that P of x. I was using this notation, okay? X is in E if and only if Px. But in this case, if we want to apply the concept of quantifiers, it basically just needs to use the implicit for all x outside of the original definition. So if I want to say that we want to create a set, okay, where elements that meet the requirement of P of x are elements inside this particular set, and everything in the set has to meet this requirement, then we could just say that for all x, which applies to everything in the entire universe, then we just then we say x is an element of E if and only if P of x. So it just makes it slightly more clear. If you want to describe the empty set, okay, so if set S is empty, then you can describe it as it is not the case that there's at least one thing that is an element of S. Okay, so that's another way to describe an empty set. Intersections and unions are quite easily defined. We just basically add a universal quantifier on the outside. So now we say x for all x is an element of A intersecting with B if and only if x is found in A and x is also found in B. Union is really simple because all it does is to change the conjunction to a disjunction. Cartesian product is a little bit more funky because it has to be nested. So we have a for all x in A that is on the outside, and then the for all y in B in the inside. So you can kind of look at this as a double loop. Okay, it is a nested loop. Then we say xy as a two tuple is in A Cartesian product with B, and for all xy in A Cartesian product in B, Cartesian product in B, x in A and x in B. Okay, now they're both needed. Okay, now this one looks kind of funky because don't we just need one of them and not both of them? In other words, if we just have the first part of the conjunction, is that not sufficient? Well, let's think about it. The first part, or the left-hand side of the conjunction, all it is saying is xy is an element of A Cartesian product in B, but does it exclude things that can also be in A Cartesian product with B? It does not. Okay, so it only says what needs to be in the Cartesian product, but it doesn't say anything about the Cartesian product can only contain two tuples where the first item is coming from A and the second item is coming from B. That is why we have the conjunction here. The conjunction is basically working in the opposite direction. It is saying if you find something in A Cartesian product with B, which is guaranteed to be a two tuple, then we know, okay, that x is in A and y is in B. So you need both of these to define Cartesian product. And then we move on to subset. So in the subset notation, A is a subset of B if and only if everything in A is also in B. And then when we want to define is a proper subset of, then we say A is a proper subset of B if and only if A is a subset of B, which is defined up here, and there is one x, at least one x in B that is not in A. So here we have, basically we're revisiting the same thing that we have already visited before, but this time we apply the quantifiers to the whole thing, to every single operator. So do we have any questions? I'm just looking at the time. We have about 2 minutes left. So with only 2 minutes left, the best use of those 2 minutes is to tell you guys what you need to read for Thursday. But that's pretty easy. I know most of you know that already. We just have to continue with the sequence. Okay, so the next on Thursday, we'll start to get into the discussion of functions. But it's not the same kind of function that you learn from math, okay? Because what you learn from math is a function is defined as y equals to f of x, okay? And then f of x is just defined to have some kind of expression with x as a variable in it, okay? Well, that still works, okay? But in this class, okay, we look at a function as a particular set, okay? And there are certain requirements, in order for a set to be seen as a function. So we'll talk about that on Thursday. And then after that discussion of what qualifies as a function, then we'll start to characterize functions. Okay, there are functions that are known as injections. There are functions that are known as surjections. And then there are functions that are known as bijections. Okay, now these things they seem to be useless, and they are probably not very useful on their own, okay? So all of these things are building up to talk about something that is actually useful. So after functions, we go back to the cardinality problem, especially things that are that have an infinite number of elements, okay? So as it turns out, if you have a set that has an infinite number of elements, there are two main categories of those sets, okay? There are sets where we say even though there's an infinite number of elements, it is countable. And then there are sets with an infinite number of elements, and it is not countable, okay? So in discrete math, okay, or in discrete structure, we are more concerned about things that are countable. So L of null is a module that talks about that, and it's pretty interesting, okay? Because as it turns out, we can establish equivalencies between sets that have infinite number of elements. In other words, we can enumerate one set using elements of another set. If it is enumerable, okay, then we can call the cardinality of those two sets to be quote-unquote equivalent, okay? So this is where things can get very kind of strange, because now we can say, oh, give me the set of all natural numbers, and as it turns out, the cardinality of the set of all integers is actually equivalent to the set of all natural numbers. It doesn't seem to make sense, right? Because with integers, values go to both sides of the number line. With natural numbers, it only go on one side. But we can claim and say that, nope, these two are the same in terms of cardinality. Then you go like, wait, -1 doesn't exist as a natural number, but I have a way to map things so that they do. Okay, so that's the purpose of L of null. And then after L of null, then we continue to talk about relations, which is kind of a break of functions, but we'll see, the application of functions after we get to injection, surjection, and bijection. It is basically a language to help us describe things, okay? And one of the things that I use as an example is, how do we describe the outcome of a sorting algorithm? Something that simple, okay? How do you describe the correct effect of a sorting algorithm in the language of mathematics? And as it turns out, that requires the concept of functions, and not just any functions. It requires the concept of a bijective function, otherwise known as a bijection. So what we are doing here, okay, is we are introducing language to help us describe things that we need to describe in programming. So that gives you a general idea of why we are working on these topics, so that you don't feel like, oh, this seems pretty useless. Well, they maybe seem pretty useless at this point, but at some point, especially when we get to this part here, injection, bijection, and surjection and bijection, then we'll start to see the application of things that we have been learning up to this point. All right. So we are out of time. Okay, so we are about 1 or 2 minutes, out of time. So I'm gonna stop the live stream at this point. If you do have any questions, office hour is at noontime. So I'll come back at noon to answer any questions that you guys might have. But right now, I'm gonna go grab a bite. So don't forget the homework. Don't forget the road taking, activity. So there are 2 things you need to do. In addition, I would like you guys to be able to read ahead of me. So that make it like 3 things to do. All right. So I'm gonna turn off the voice channel and turn off the live chat. The live stream at this point.